Okay, welcome. This is our first video. Biologists often use math models to describe communities of organisms, anything from a culture of cells to a herd of zebras. These models result in functions that approximate the population of the community as it changes in time. An important question concerns the long-term behavior of these population functions. Does a population approach a steady state level, which corresponds to a stable community, as in the first figure, which should be right here? Notice over time it approaches a stable level. Does the population oscillate continually without settling at some fixed level, as in the second figure? Does the population decrease to zero, indicating that the organism becomes extinct, as in the third figure? Such questions about behavior or functions are answered using the powerful idea of a limit. Here's our chapter preview. All of calculus is based on the idea of a limit. Not only are limits important in their own right, but they underlie the two fundamental operations of calculus: differentiation, calculating derivatives, and integration, evaluating integrals. Derivatives enable us to talk about the instantaneous rate of change of a function, which in turn leads to concepts such as velocity and acceleration, population growth rates, marginal costs, flow rates. Integrals enable us to compute areas under curves, surface areas, and volumes. Because of the incredible reach of this single idea, it is essential to develop a solid understanding of limits. We first present limits intuitively by showing how they arise in computing instantaneous velocities and finding slopes of tangent lines. Okay, you should know what tangent line is in calculus, hopefully. As the chapter progresses, we build more rigor into the definition of a limit, and we examine the different ways in which limits exist or fail to exist. The chapter concludes by introducing the important property called continuity and by giving the formal definition of a limit. Okay. This brief opening illustrates how limits arise in two seemingly unrelated problems: finding the instantaneous velocity of a moving object and finding the slope of a line tangent to a curve. These two problems provide important insights into limits, and they reappear in various forms throughout the book. We'll start with average velocity. And this problem here talks about you want to calculate your average velocity, and you check your, when you pass a milepost 100 at noon and a milepost 130 at 12:30 p.m., you've traveled 30 miles in half an hour, so your average velocity over this time interval is 30 divided by 0.5 is 60 miles per hour. But in contrast, even though your average velocity might be 60 miles per hour, it's almost certain that your instantaneous velocity, the speed indicated by your speedometer, varies from one moment to the next. So example 1, average velocity. Here's an example using the gravity function as far as position. So a rock is launched vertically from the ground with a speed of 96 feet per second. Neglecting air resistance, a well-known formula from physics states the position of the rock after t seconds is given by this function. This should be familiar. The gravity, negative 16 feet per second, times t squared, plus the initial velocity, which is 96 feet per second, times time, plus 0, which is your height, initial height. Okay? So here is how we'd compute this. The position S is measured in feet, with S is 0 corresponding to the ground. Find the average velocity of the rock between each pair of times. Well, what would we do? We'd plug in 3 to this function, get a number here, like S of your time 3, and then subtract S of time 1, okay, and divide it by what? 3 minus 1, okay? And we do the same thing here. In the example here, if they want you to for a quick check, you should be able to figure out, I'd plug in 3, S sub 3, and this T sub 1 just represents time. This is your initial time, this is the second time, okay? Alright, and here's your difference in time. Okay, so in this quick check, we would want the average velocity between 3 and 2, no different than these problems here. Plug in 3, get your number, that would be this. Plug in 2 squared, and you figure out when t is 2, when you get this value, your output, and then divide that by 3 minus 2, which would be 1, okay? Example 1 demonstrates that average velocity is the slope of a secant line in the graph of the position function, that is this position function. This right here, the average velocity, this is the average velocity. It's also going to be the slope of the secant, okay? All right? So here's your, let's say 3 seconds. You plug in 3, this is your output. You plug in 2 or 1, whatever your other time is, and that's your output. And notice, here's your secant line between those 2 points, okay? And that's your average velocity. The average equals the slope of the secant line between these 2 points, okay? V average equals the slope of secant, which is position function of time sub 1 minus time initial, t sub 1 minus t initial, okay? Here's your change in position, okay? Let's take a look at instantaneous velocity now. To compute the average velocity, we use the position of the object at 2 distinct points, this time and this time. How do we compute instantaneous velocity at a single point in time? As illustrated in the example 2, which is below us, the instantaneous velocity at point t equals 0 is determined by computing average velocities over some interval from the initial time to some specific time that decrease in length. And what we're saying is we're going to compute average velocities over this interval, and we're going to make this interval smaller and smaller and smaller till it approaches very close to this initial velocity t0, okay? As t1 approaches t sub 0, the average velocity typically approaches a unique number, which is instantaneous velocity. This is our limit, okay? All right, explain the difference between average velocity and instantaneous velocity. Let's check this. Average velocity is the velocity over an interval of time. Instantaneous velocity is the velocity at one point of time. So here's example 2. In a language to be introduced in the next section, we say that the limit of the velocity average as t approaches 1 equals the instantaneous velocity, v instantaneous, which is 64 feet per second. This statement is written compactly as v instantaneous equals the limit of the velocity average as t approaches 1, and that equals this. The limit as t approaches 1 of this the average velocity, okay? Position at one time minus position of the another, position of t minus position at time 1, and t minus 1, it should be equal 64 feet per second, okay? Here's your, all right? Let's take a look at this. Notice right now we've got position function at 2 seconds minus position at 1 divided by 2 minus 1 gives us 48 feet per second. Notice now we've changed, we're making this interval smaller. Now it's 1.5 seconds to 1 second, and that approaches 50. That equals 56 feet per second. Now look, interval's getting much smaller. The position at 1.1 seconds minus the position at 1 second, and here's 1.1 minus 1. That's 62.4. Now look at our interval now. 1.01 to 1, 63.84. The interval gets smaller. T equals 1 and to the t equals 1.001, and it's approached now to 63.9. And this interval gets even smaller. T equals 1, and the other t is 1.0001. And notice how close it is to 64. Okay? Notice the different slopes here of the line as we connect these points. It gets a little shallower here. Okay? All right, slope of the tangent line. Several important conclusions follow from example 1 and 2. Each average velocity in table 2.1 corresponds to the slope of a secant line on the graph of the position function in 2.5, figure 2.5, okay, which is right here, okay? All right? Okay, so let's go repeat that. Each average velocity in table 2.1 corresponds to the slope of a secant line on the graph of the position function down here in figure 2.5. Just as average velocity approaches a limit as t approaches 1, the slopes of the secant lines approach the same limit. It's going to be the same because, all right, average velocity approaches an instantaneous velocity. The slopes of the secant lines approach the same limit as t approaches 1. Specifically, as t approaches 1, two things happen. The secant line approaches a unique line called a tangent line. Let's look at this note. We define tangent lines carefully in 3.1. For the moment, imagine zooming in on a point P of a smooth curve. As you zoom in, the curve of P is more and more like a line passing through P. Okay? The line is a tangent line at P because a smooth curve approaches a line as we zoom in on a point. A smooth curve is said to be locally linear at any given point. Okay, that's kind of obscure. I think you guys know what a tangent line is, all right? The slope of the secant line, m secant, approaches the slope of the tangent line at point 1, function of 1, s of 1. Therefore, the slope of the tangent line is also expressed as a limit. Okay, the slope of the tangent line equals what? This limit of the secant line as t approaches 1. Okay, and here's the position function we talked about as t approaches 1. All right, notice here's t is 2.4, here's 2. Notice as t comes, here's t and here's the function value, okay? This purple line, tangent line here is the slope of the tangent line is 64. This blue dot is this t level. It's 1.9, 1.85, 1.58. These are all, notice these secant lines, there has different slopes. As like I said, if we get, this is a greatly different slope at, this secant line here. But as t gets closer and closer and closer to 1, notice how the secant line approaches the tangent line until as t becomes 1, voila, we're pretty much there. There we go, 1.01, that's close enough. Notice we've got the same line. The secant line is the tangent line, okay? All right, the slope, so the two things that happen here, the secant line approaches a unique line called a tangent line as t approaches 1, okay? The slopes of the secant line, the slopes of the secant lines m approach the slope of the tangent line, therefore the slope of the tangent line is also expressed as a limit, okay? All right. Quick check 3. In figure 2.5 is the slope of the tangent m tangent at t2 greater or less than the slope at 1. Well, here's the slope here at 1, and what happens to this? What happens to the slope as t approaches 2? Approaches 2, it flattens out, so the answer is it's less than. Okay. All right. The parallels between average and instantaneous velocity on one hand and between slopes of secant lines and tangent lines on the other illuminate the power behind the idea of a limit. As t approaches 1, slopes of secant lines approach the slope of a tangent line. As t approaches 1, average velocity approaches instantaneous velocity. Figure 2.6 summarizes these two parallel limit processes. These ideas lie at the foundation of what follows in the coming chapters. Okay? So notice here's average velocity. Okay, notice this is between what is time, is the difference between t equals 1. Here's 2.3 seconds, and here's 1 second. As we start averaging time, the interval between time gets smaller and smaller and smaller. Now it gets closer and closer as the interval, as t approaches 1, voila, the velocity, average velocity approaches instantaneous velocity. The secant line approaches the tangent line. Okay? Instantaneous velocity at t equals 1 is the limit of the average velocity as t approaches 1. The slope of the tangent line at 1, 80 is the limit of the slopes of the secant lines as t approaches 1. Okay? And you'll have some exercises, but for now I got to wrap things up. Hopefully, I'm doing a lot of this because you probably don't have your textbook yet. But this ought to be pretty good review to help you do your problems, okay? All right, you're going to have exercises such as this, basic skills, and more of the same. Okay? All right. Welcome to class. We should have a good year.